Solid state. There are three types of bonding that can produce solid, which is ionic bonded solid, metallic bonded solid, and covalent bonded solid. All solid ionic compounds are arranged in a crystal lattice where the positive ion is positioned next to the negative ion. They do not conduct electricity in solid state. However, when dissolved in water, they are able to conduct electricity due to the presence of freely moving ions. Since the electronic force between the positive and negative ions is rather strong, they will have high melting and boiling point. The strength of electrostatic force in a crystal lattice are determined using lattice energy, where it is the energy to break 1 mole of ionic compound into its ion. The two factors that affect lattice energy are the size of the ions, where smaller ions will make the ions closer to one another, which in turn make the attractive force stronger, and secondly, charge of cation, where bigger charged cation is smaller in size, which consecutively makes the attractive force between the cation and anion stronger. Metallic bonded solid are solid lattice with an attraction between the positive metal ion and delocalized electrons. Because of the presence of delocalized electrons that will make sure no repulsion between likewise charged or positive metal ions, these type of solid are able to conduct electricity in solid or in molten, and they are malleable and ductile. Because they will always have electrostatic force between the positive metal ion and delocalized electron throughout the lattice, a lot of energy is required to melt or boil them. However, metals are mostly used in combination with non-metal in alloy due to stronger properties. For example, brass is used to make musical instruments. Because the presence of different size atoms in the lattice prevent the layers of ions from sliding when force is applied. Aluminum alloy often employed in making airplane because of its lightweight and corrosion-resistant properties. Although most molecules with covalent bonding are either gas or liquid at standard temperature and pressure, there are some that appear as solid due to several characteristics. There are three types of covalent bonded solid, which are hydrogen bonded, giant molecular, and simple molecular. The example of hydrogen bonded solid will be H2O. For giant molecular solid, we have diamond, graphite, graphene, and silica. And for simple molecular solid, we have Buckminster fullerene, iodine, and carbon nanotube. The attractive force responsible for the maintaining of the ice lattice is hydrogen bonding. Because of the extensive hydrogen bonding in H2O, it can appear as solid at specific temperature. In ice, the water molecule forms 4 hydrogen bonds with neighboring water molecule, creating a repeating tetrahedral structure. This pattern causes the ice to have much greater openness in the structure, which makes ice floats on water. Giant molecular solids are big molecules with extensive or covalent bonding in its structure, which make them to have a high melting and boiling point. Diamond and graphite are allotropes of carbon, which is structurally different form of the same element. The carbon in diamond is sp3 hybridized, while in graphite is sp2 hybridized, which causes graphite to be able to conduct electricity due to the presence of delocalized electron in unhybridized p orbital. The layers between graphite is connected by London dispersion force. Graphene is a single isolated layer of graphite. It has a better electrical and heat conductor than graphite, which make it potential substance for many applications, while silica or silicon 4 oxide is the main composition of sandstone. They are insoluble in water with high melting and boiling point due to the extensive covalent bond in the structure. Any other covalent bonded solid falls under the category of simple molecular solid. For example, iodine I2. The attractive force that keeps iodine as solid at standard condition is London dispersion force. But because it's just a weak force, iodine appears as a soft solid with low melting and boiling point. But Mr. Fullerene and carbon nanotubes are another example of allotrope of carbon. Discovered many years back and still developing, they have several promising potential in industry.